And welcome back. Today we're going to be talking about ways to control electricity flow in the form of relays. As you can see on my workbench, I have 3 breadboards, each with a different type of relay on it. Each one has its pros and cons. Some of them will only switch AC, some of them will be safer than others, some will protect your Arduino. In fact, there's so many things going on here. Let's get cracking on straight away, and let's talk about the one at the back here. That's a fairly standard, what we'd call traditional relay, I think. Yeah, traditional I think is the right word. Okay, before we do that, a word from our sponsor. PCB Way, PCB prototyping the easy way. New members get their first order absolutely free. Check out their online site now. Right, so here we have the traditional relay, as I call it, although it's not quite as simple as that. If you want the full details on how to use sort of relay, because I'm not going to go through every single nuance. I did a video, number 18, way back, and it went into the nth detail of how these opto relays actually work. Primarily, you've got your relay here mounted on a little board, but you could, of course, mount the relay directly onto some kind of PCB, or a Veristrip, something like that, and control it directly from Arduino, but I wouldn't recommend it. This way, using an opto coupler here means that your Arduino, or whatever it is you're driving this relay, is pretty much protected against anything that could go wrong with this relay. And given that the relay can drive mains, if you so want it, up to 250 volts AC, you may well think that the extra protection is what you need. Now, of course, if you're only driving, say, 12 volts here, you might think, it's a bit of overkill, and I'll plug this relay, just this blue unit, directly into my circuit. Fine. Okay. But I would say, look at video 18, see all the ins and outs of this, and I'll give you a quick summary now of what this unit is doing and why it is a better solution than just a plain old relay. Let's see it in working then. So what I've got here is the relay powered up with 5 volts, as you can see on the top and bottom rails here. The light's on here. That little black thing in there, that is in fact an opto coupler, and I'll explain what that is in just a sec. But if I bring this input lead now to the positive supply, imagine your Arduino or other microcontroller delivering 5 volts into this. As you can see, the LED here goes on. There's another LED on board that goes on. And that's it. That's how it works. And you can probably hear it clicking. A bit like the indicators in your car. Okay, and that's it. There's nothing fancy about it apart from the opto coupler. So let's just have a quick circuit diagram of that before we move on to the next one. Right, let's draw then on this board what we mean by opto coupler. You have your relay coil here, and normally that would be energized by a 5 volt supply, for example. Now you could drive that from your Arduino directly, possibly depending on how much current flows through here. Remember, your Arduino is limited to 40 milliamps absolute tops, and really you want to keep it down to 20. So you might have to use a transistor, an NPN transistor or something to drive this anyway. The problem is that this is then connected directly into your circuit, and that's not considered a particularly good thing. Let's not forget also your protection diode across here to avoid all those flyback voltages. Okay, that will protect whatever is connected to the other side of here. The back EMF, when the power is dropped from here, there's still energy in this coil, and that energy's got to go somewhere. And if you don't have this diode wired up across that coil, it's going to go back into your circuit, and that is the end of your Arduino, at least that port anyway. So why should we have an opto coupler on here then to make things a little bit safer? Well, if we imagine an opto coupler in there and your Arduino over here delivering something on some kind of GPIO port here, ideally that goes into the opto coupler, and then this might be grounded. This wiring arrangement differs depending on which type of relay you've got, but basically inside that little black opto coupler, all you've got is a light emitting diode. There it is with an arrow. So that's a light emitting diode. Okay, there's probably on board, there could well be a resistor here, I would imagine. Okay, something like a 200 ohm resistor or something. So that your Arduino, all it ever sees is a light emitting diode, a LED. Pretty much like the blink circuit. That's all your Arduino is aware of. The other side of this, some opto-sensitive transistor, you don't really care about anymore, because what happens on this side, you don't care. All you know is that when you fire in voltage into this side magically works, and somewhere on your relay switch, that suddenly goes from open circuit to closed circuit. Sometimes it can flip-flop, as in fact the one I got on my bench, so that if that was normally open, you might have one the other side as well, and that would be normally closed. In fact, that should have been drawn so they were touching. So you could have normally open, normally closed. But the point is, whatever's happening on this side, you're not really too bothered about. And it's the optocoupler that does the magic. Okay, so that's a very quick summary. As I say, look at video 18 if you want the lowdown on this. And I think that's where we're going to leave the standard relay, because it really is so simple. And it's simple to use as well. I mean, obviously, you just bring that input high, the relay energizes and switches the output. Now, the output is a voltage-free contact, which means there's no voltage on here other than what you put on there. So you could have it for signaling. You could have it, for example, grounding a pin somewhere of something else. But normally you'd have voltage on there, and that's how it works. Great. Simple, straightforward. Want the detail? Look at video 18. I'll put a link in the video, and at the end of this video I'll have one of those video boxes where you can click on it and go straight to the video. I can't remember what they're called. Okay, let's move on then to something a little bit more exciting. When I say exciting, I do mean death-defying in some ways, because this is now connected up to the mains. Yeah, 240 volts. That's what this bit here is. Okay, now it's all perfectly safe as it is, all nicely insulated, but I'm not going to get too close to this side of things. Now, this is a solid state relay, and generally they switch AC voltages only. Yes, apparently there are some that can switch DC, but I've not got one, and I can't find one anyway to get, and I suspect they're probably specialised. Let's just see how this works though first. Let's get it working, and then I can disconnect it and feel happy that I'm not going to kill myself or something. So by bringing this input now low, that's the way this particular module works. By bringing it low, as you can see, my desk lights up, and the video camera goes mad trying to stabilize the color and all that. So that's what's happening, right? Now you can't hear any clicks. What you can see, if I get my little pointer on there, you can see a little red LED lighting up in there, which shows that it's on. Okay. Now, as I say, normally solid state relays switch high AC voltages in general. Yes, of course there are exceptions, but this one, for example, can switch 100 to 250 volts AC at a maximum of 2 amps. Well, I'm driving something like 1/10 of an amp on this because it's actually driving an LED lamp, but well, it's simple enough to use, pretty similar in some ways to the previous relay we saw, except there's no mechanical parts in here. So if you want to switch this on and off, 20 times a second, well, you can basically, because there's no delay between actually switching it on and it switching on, nor in switching it off. In fact, the actual delay is something like 1 millisecond plus half a cycle or something like that. There's a whole spec sheet we might look at a bit later on. So that's a solid state relay, but how does that actually work then? All right, I can tell you for a start that on here there is another optocoupler to protect this side of the circuit, the bit that I'm touching, to this side of the circuit, which I most certainly don't want to touch because it's connected to mains. So optocoupling does seem to be a theme running through here, doesn't it? Because the manufacturers of these modules do want to protect the circuit that's driving this particular module. But apart from the optocoupler, what is this actually doing? How does a solid state device actually work if there's not a physical contact somewhere? Time for a drawing. Right, solid state relay, SSR, in its simplest form, perhaps slightly oversimplified, this is what's happening inside a solid state relay. We have once again our inputs going into some kind of LED, right, an opto LED, so that's giving out some kind of light. Now the other side is going to be something that's light sensitive to that LED, but in this case it's not a phototransistor, it's actually a phototriac. If I can draw this correctly, well, that's about it, I think. Yes. So we have our inputs like that and our output with this triac. This triac controls mains voltages, and if you like, it's two diacs back to back. Obviously it's made as one unit, but the power, AC power, remember, on here, the positive supply, positive cycle goes through one way, the negative the other way. That's how the AC flows through this. And then you have your load, your lamp, or whatever it is, and your 240 volts or 110 or whatever at this end. Fine. So as long as there's a light here, then this sensitive piece of semiconductor will conduct and light your light exactly the same way as what I just showed you. Now there's a bit more going on in here than what this diagram actually shows. So let's just draw a couple of other things in here. So I've drawn now the same LED, and now we do have this phototransistor or something, basically some kind of optocoupling going on in here, but there's more to it than just firing off power to the triac. First of all, we have something called a zero voltage detection circuit, and I'll come on to that in a second. Once the zero voltage detection decides now's the time to switch on, that then goes on to the actual trigger circuit, and that in itself goes on to driving the triac as we drew before. The triac has an input to it. I don't think it actually should look like that. It should look more like that. And there we have our 2 points for connection for the main circuit. So this trigger here and the zero voltage detection and the optocoupling is what you get when you end up with one of those solid state relays. Now, what is this zero voltage detection and why is it important? For that, we need a final drawing, and then you'll understand everything you need to know about solid state relays. So, zero voltage detection, why is it important? Well, imagine now that your mains supply or household supply, whether it's 50 Hertz, 60 Hertz, 110 volts or 220, it's AC and it looks like that. Well, hopefully it looks a lot better than that, but that's the best I can draw it. Now, this is fine, and this is what goes through whatever device you're trying to control the power, and in this for this particular relay it's either an on or off state. We're not trying to dim anything here, that's a whole different kettle of fish. Okay, so we're trying to turn something on or off. Now if your optocoupler part of the circuit driven from your Arduino or Pi perhaps with a transistor or whatever microcontroller you have, let's draw that in red. If your DC component is coming in and suddenly it says, oh, I want you to switch on now at that point and then stay on until, I don't know, there. That's the sort of time I want you to stay on. All right, it's a little bit artificial because we're only talking about one cycle here, but it gets the point across. At this point here, your AC voltage into your house, and we'll stick to the 240 UK voltage at the moment, the zero voltage detector says, I can't possibly switch on at this point, your output, because if I was to switch on here, I would create so much interference, we'd fail any kind of electromagnetic interference test. Okay, it's got to wait until the voltage on your supply drops to zero, or pretty much, you know, within a few tens of volts of that. Once it drops to zero, it goes, now I'll switch your output on. And ditto, when you say I want the voltage now to go off at this point, it goes, well, I can't switch it off here because once again, I could possibly be 200 volts there or something like that. I can't switch off here. That abrupt switch off at that time would create a lot of interference again. So once again, it waits until the 0 voltage has been reached at this point, and then it says now I can switch off. And if you think, oh, what about all this delay? Look, you're only talking about 1/100th of a second for that half cycle, and ditto for this. So the maximum you're ever going to wait is less than 1/100th of a second before it decides it can switch on here and off here. The time element is just not important at this stage at all. But what is important is that the switching occurs at the 0 volts to stop any kind of interference. Otherwise your neighbours will come banging on your door saying, what are you doing to my Wi-Fi and everything else in my house, because all I'm getting is this static interference from everything. And of course the point being that any manufacturer that didn't have 0 volts detection like this would be creating so much interference it would never pass any of their laws or standards. Okay, so that's the 0 voltage detection pretty much in a nutshell. Your on-off could be delayed by as much as half a cycle, and your solid state relay works without any moving parts. So therefore it is, of course, well, a bit more robust, isn't it? What else can we say about the solid state relay? Well, the best place to go for information about the solid state relay is, of course, the datasheet, which is easy reading in this case. Let's just whiz over to the browser. Here we are. This is the actual datasheet for the Omron relay on that board. And what does it say? Well, let's have a look. The bottom is approximately 3 times smaller than G3M. I wish my bottom was 3 times smaller, but that's a different story. I don't really know what that line means, to be quite honest. Low cost, yeah. Built-in snubber circuit, hooray! What's a snubber circuit? It's basically a resistor and capacitor in series across the output to stop any high voltage, well, transients really. Okay, that's all it does. You'd have them on a standard relay possibly to stop any arcing across the contacts. Let's have a look. What else? Okay, the one I've got then. So this photo triac is how it's isolated. It's 0 crossing, yes. It's got a built-in resistor for the input voltage, so you can put the full 5 volts on. It's got a built-in snubber circuit, yes, and it can carry 2 amps at anything from 100 to 240 volts AC, and the version I've got is a 5 volt DC version. Obviously, as you can see here, there are other voltages available, and in fact there are non-zero crossing versions and all sorts of things. But so be very careful if you're going to get one of these. Make sure you get the one that I got, which was in fact this one here. There it is. So as you can see, it's pretty cheap, isn't it? Yeah, so 70 pence plus 18 pence shipping, so 88 pence, less than £1. That's pretty good. Although we do have to bear in mind that it has only got a 2 amp rating, whereas the mechanical relay had a full 10 amp rating at 250 volts AC. Yes, now this is something else to think about, of course. This is a semiconductor device. It's not a mechanical switch, which then, when it's off, it really is off. You know, there's a gap in the power supply. Here it's all done with semiconductors, so you are going to have a leakage current, as it says here. A leakage current, small though it may be, well there it is, 1 milliamp at 100 volts AC or 1.5 at 200. So I'm guessing at 240, which is what I'm running at the moment, it's probably going to be in the region of about 2 milliamps leakage. Which means, of course, that when it's off, you still can't touch that output terminal because potentially you're going to electrocute yourself. Well, you won't electrocute yourself at 2 milliamps, but you know, there's still mains potential at that output, even though you think it's off. So it's something to think about. Well, here's the ratings. So I've got the G3MB 202P, that top one, and it says 2 amps, 240 volts, say for general purpose. For tungsten, it drops down to 1 amp, and for a motor, 1.6 full load amps, 9.6 locked rotor amps. That's what that bit stands for. So basically, at the instant of switch on, the rotor's not going round, is it? So you can have a massive inrush current before it starts spinning. Now, it's going to spin very quickly, a motor like a drill or a lathe or something, but it is limited to 1.6 full load and 9.6 for that inrush. So all these things have to be taken care of and thought about if you're going to use an SSR. In normal circumstances, such as a light, you got no problems at all. Right, what's next? Now, this one is the one that generated the most interest for me. This is what is known as a bistable or latching relay. And, hands up, I knew nothing about this. And it all came about due to a comment that was placed on one of my videos. Let's have a look at that. So on this video, there was a comment by Bob. Thanks, Bob, for putting this up here. It really made me stop and think. What Bob says here, especially this bit, he says, enter the standard bistable or so-called latched relay. This works by using 2 coils, etc., etc. Now, you can go back to this video and read this comment, or pause the video and read it here if you like. But I thought, what do you mean bistable latching? This I must look at. So, what do we mean by bistable relay? Right, a latching relay then. So what have we got? Now, in a normal relay, what you've got is a coil and an output. Right, so that's it. 1 coil, 1 output. You apply power on here. The relay flips over magnetically and joins these 2 contacts. Bob's your uncle. You release the power. The relay springs back, because there is actually a physical spring in the relay, to bring it back to its original state. A latching relay works a little bit differently. So what you've got in a latching relay are 2 coils. There we are. And you've got, in this case at least, you've got a switchover contact. So you've got one which is normally open and one which is normally closed. Okay, so normally closed, normally open, and this is the power in. So if you were to put 5 volts in there, it would switch it there or switch it there. Okay, and into these coils you would put, well, they go to ground one side, and you probably put +5 into both of these here. So what happens is when you initially switch this relay on, the normally closed, if you can, it's a bit awkward saying that because it depends on what the last state of this relay was, but assuming the relay was left in this particular state, this one would be on, right? So this here would have your positive on, and assuming that this coil made it switch into that state, applying power to this coil again would not make that move. It would have this contact, and that's where it'd stay. Now if this other one, let's use a nice different colour, if this one here controls the state of that other one there, by applying power here, it would cause this to flip the other way and then stay there. You can then remove the power. That's the whole point. You remove the power and it will stay that way until you apply the power back on this coil again, and it would flip the other way. So each of those coils causes this to either go that way or that way, and it stays there. Latches, hence the name. Also called a bistable relay, but I think latching relay covers it a little bit better. Okay, so now we've seen how we have 2 coils causing that switch to go either way, and it really is a switch just like that, just like a normal relay, no solid state stuff here. This is a physical relay. Let's see it in action. Right, so I've powered up the circuit, and I'm only using one of the switches, by the way. There's 2 on here, but they are identical. So I'm just ignoring this switch here, and I'm just concentrating on the one at the back. So powering it up, one of these LEDs has come on, and the 2 coil powers are supplied by the red and the black, and as you can see at the moment, neither is connected. So if I was to connect the brown again to the positive supply by connecting it into the breadboard, nothing happens because it's already latched that way. So basically, by disconnecting, we're no longer drawing any current from the power supply or battery or whatever, and well, that's a good way of saving power, isn't it, as Bob says in his comment. Now if I want to switch the other way, all I have to do is connect the other coil now to the positive supply, and you can see the LED has now switched over to red, but more importantly I can disconnect that coil and it stays that way. More to the point, I can actually disconnect the entire power. So there we are, we've now disconnected the power entirely, and when I connect back up again, it's remembered which way it was, or it stayed in the same way, more to the point. There's no memory involved as such, and the red one's still on. So connecting the red to power has absolutely no effect because we've already switched in that way. It's only by connecting the other coil, the brown one, which will connect into the yellow, and click. You might have heard that click. Let me do it again, you'll probably hear it. Click. What they do say is do not supply power to both coils simultaneously. I've not done it, I'm not going to try it, I'm not going to see what happens, because I'd like this to actually work in the future for some future project. Alright, I don't want to destroy it just for this demo. I'll let others do that. So there we are, a latching relay that can save power. And if we go back to that video where Bob actually made his comment on about saving power, this one here, could we replace the MOSFET that I eventually used with this relay? And the answer is yes, you could, because the Arduino would power up one of these coils, and only one, depending on what you want powered up, where you want the switch position to be, and then immediately remove it. So how much power would it take to actually energize this, and for how long do we have to keep the coil energized for that mechanical movement to actually happen? Well, for that, once again, we need to look at the datasheet. Right, so the datasheet, the bit we're interested in is this operate time down the bottom here, and the release time, and they both say, well, 4.5 milliseconds and 3.5 milliseconds, which is quick. It's not instantaneous. It's not like a MOSFET. We could probably do it in, microseconds, but it's pretty quick. It depends on what you're doing with it, of course. And once again, because it's a mechanical device, it will have a lifetime associated with how many times you actually switch it. I mean, yes, it could be hundreds of thousands, if not millions of switches, but it will have a lifetime. And the one downside of this particular switch is that it can only switch 125 volts AC. Although there's a little bit of discrepancy here. On the actual device itself up here, if I just make that nice and big, you can see it. It says 1 amp at 125 volts AC. But then it says maximum switching voltage 250 volts AC or 220 volts DC. So I don't really know what that's telling us. Maybe you guys out there will know. Those are the experience of this one. In fact, Bob, you might know. I don't know if we should really switch 250 with this. I don't think I'd put it into circuit with that when it says 125 volts all over it. But there's probably other latching relays like this one that can handle higher voltages and higher currents. So just be careful what you're buying if you go down that route. Cool. Well, I think that's absolutely massive. So big thanks to Bob there for bringing to my attention that this device even exists. I didn't know it did. My relay knowledge stopped at a standard mechanical relay on or off and the SSR. So I've learned something, and I hope this video has brought some more knowledge to you guys as well. Great. I think we'll leave it there for now. Anything else you want to say, comment on, put it below the video. Remember, YouTube likes it when you guys comment. And well, we'll see what the next video brings. In the meantime, thanks for watching. See you in that next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.